today's robots have got like shed loads of compute thrown at them, stacks of GPUs, you know, all these vast billion parameter LMs, and they're still really clunky compared to animal bodies. So I'm thinking we're missing a trick here. So I'm a Programme Director at ARIA, which is the UK's Advanced Research and Invention Agency. It's a new government funding agency with a mission to fund breakthroughs in science and technology which will benefit society.
So I want to start right away and ask you, what are you working on?
I'm working on robot dexterity, so giving robots the ability to precisely and delicately manipulate objects and apply forces to them.
So why robot dexterity? I mean, why do you choose that particularly thing about robotics and what makes it like special?
I think it really unlocks the power of robotics to help society. So pretty much everything you can think of that you might want robots to do for us, whether that's assembling electronics or making a sandwich or waste disassembly, sorting, they need to be able to manipulate objects precisely, including objects that are deformable or delicate or can be damaged. And that's something that's really hard for robots today.
Why is it hard, right? Because I mean, we're humans, we say, okay, this should be an easy thing. Why? What makes it so hard?
Yeah, that's a great question. I think there's a number of things. If you look at, human hands, I don't want to be too locked on to robot hands have to be like human hands. I think that's an open question. But our hands have got many degrees of freedom. We can move our fingers in lots of different ways. People say hands have got 27 degrees of freedom. So if you're trying to make a robot manipulator with that many ways it can vary, that requires a lot of motors.
Right.
And so now your hands got really heavy and bulky because you've got all these big motors. So that's one challenge. Another is that at the moment, robots typically don't have a sense of touch. So if you think about doing anything delicate yourself, like trying to tie your shoelaces while being unable to feel your hands, that would be really hard, but that's what we're asking robots to do today. So I think there are lots of reasons it's a really challenging problem.
Right. Let me go one by one. You mentioned the first one is you will make the hand very heavy, right? But that's because of the materials we are using now. So how do you solve, what are the exploration areas you have in that challenge? Are you looking for how can we bring new materials? How can we bring different ways of articulating the hand? Because you talk about the shape also, and it can be a different way. On the other hand, you were talking about the 27 movements that you have. But I'm guessing also the sensitivity, right? It's the nerves, it's the connection and understand the sensitivity that you have on that. So what are the areas that you think you are working on or you're exploring that are more interesting right now?
So one of them is new actuators, new motors essentially, to enable robot hands to move better. And what you want, you may need strength if you want a robot to turn a screwdriver or something. So you want to be strong, but you also, as you say, want to be very delicate. So you need to be aware of the force that you're applying, and you need proprioception. You need to know where the different parts of your hand are. So we're funding work into new actuation techniques, and as you say, using new materials, trying to produce motors that act more like muscles, more like biological muscles, but made out of artificial materials.
You mentioned funded, so I want also to give the audience the background of what is the framework of what you do, because you are actually working for one of the most innovative and advanced agencies that is doing something related to moonshots and frontier research, but it's a very innovative agency in the UK that gives a lot of freedom for looking into new areas of research and have a very unique way of designing that. So can you explain a little bit more how this works for you and your area? Because you say robot dexterity, but what does it mean in your program? And what are the areas that you are framing?
Yeah, definitely. So I'm a Programme Director at ARIA, which is the UK's Advanced Research and Invention Agency. It's a new government funding agency with a mission to fund breakthroughs in science and technology which will benefit society. And we're a high-risk, high-reward agency, so we're very much up for funding moonshots that may not work out, but if they did, would be huge.
Do you have to look for something that will have an impact in society, or it's an impact on the future of technology? Or what are your criteria to find what do you do? And how do you come up with this one? Because I believe that it may or may not have a connection with your previous research.
Yes and no, that's right. So ARIA has this mantra of we look for research that is important, underserved and ripe. So important is all about the benefit for society. So we don't just fund like pure curiosity-driven research with no possible, without reference to the benefit. We are looking to have a positive impact on society in some way. But within that, we're willing to fund very basic, low technological readiness level research. You mentioned my previous background. I trained originally in physics, and then I worked for many years in computational neuroscience. So I came to ARIA without a background in robotics.
Right.
Yeah, but I developed this conviction that robotics is really important and became very excited about funding it and developing the research there. And I think it is amazing in giving us the opportunity to do that, giving programme directors the opportunity to fund work outside their own area of expertise. So ARIA recruits programme directors who all have a very deep area of technical expertise, but it doesn't constrain them to work within that area, because it believes that magic can sometimes happen when somebody moves outside their area and goes with fresh eyes and the freedom to ask all the dumb questions. And I have really enjoyed that freedom in robotics.
So how did magic work for you? How did you went into, this is what I've been doing before, I've been looking into, it was more neuroscience related, and then suddenly you think, it's going to be robotics dexterity. How the process goes into that?
So maybe it's worth giving a little bit of background of what got me thinking about robotics. And that was, I'd worked in visual neuroscience for many years, mainly in stereoscopic vision, mainly in humans and other primate models. But I'd got interested in stereoscopic vision in insects. So I should explain, stereoscopic vision is the perception of depth and distance that we have by virtue of comparing the images in our two eyes that see the world from slightly different viewpoints. And I was working on praying mantis. So the praying mantis is an insect that has the ability to perceive distance, and it knows when to strike at its prey based on stereopsis. So I was trying to understand the computational algorithms that happen in the mantis brain to enable them to do that. And I think because insects are just simple creatures, and yet they achieve amazingly complex behaviour, it felt very natural to me to think of them as little robots. Yeah. And I'm trying to reverse engineer how this robot works. So I was thinking more and more about robotics, about control systems, about the interaction between the visual input, but also the active, the animal's movements directing the vision. So that's what got me thinking about robotics to begin with. And when I came to ARIA, I thought I would love to fund some research in robotics. And so I went out and talked to an awful lot of people in the field, in the UK and beyond, in academia and in companies. And I became aware that there was this gap in the hardware, that there's so much excitement at the moment about what's unlocked in robotics because of AI and the new control policies that are opened up. And that's great, and I completely buy into that. But they're currently doing it with really very old-fashioned hardware.
That's true.
Yeah, and you look at the robots that were maybe teleoperated back in the 1950s, they're not that different from the robots that you see in the 2020s, which is kind of amazing. And people would say to me, well, that's because the limit isn't the hardware, the limit is the control system. You can teleoperate a robot to do lots of complicated things, but we don't know how to have it do that autonomously. Right. Therefore, the hardware is fine, the problem is the control. And I think that has been true, but I don't think it's going to be true for much longer because of the advances in AI. So in my research programme, I'm trying to get ahead of that barrier and say, let's fund work now in novel hardware so that in 5 or 10 years' time, when people really bump up against the limits of what's possible with today's hardware, they'll have all these new components available to them.
I want to also ask you a specific question from your research, because you are talking about this vision and sensing, and you're going into dexterity of hands, right? But it has to do a lot of sensing too. Maybe not with the vision one, but it also has to be with the sensing. You talk also about data with robotics and the part of physical AI that now everybody is talking about. We had amazing advances with AI. The LLMs have been like exponential changes. But we also are at a moment that it seems that we are plateauing into the scale of what LLMs can do. When it goes into robotics, most of the people that say is, well, it's different. The data is not as infinite or large as LLMs were before, because it's a complete different set of data. It's the real world. And by the way, you cannot be learning as you are learning in LLMs, because if you make a mistake, it's a very dangerous mistake. It's not something that you just erase something in the topic. So we also have that problem with data. We have the problem with sensors and getting that part. So how all of that, how those challenges, how do you see them now, updating it to today, given what you've learned also with the Dexterity, how do you see the robotics challenges evolving?
That was a big question. So let me focus. Yeah, lots of things. I'll focus in on one aspect to begin with, which is the sensing. So it's kind of ironic. I spent most of my career working on visual neuroscience, but frankly, in robotics, vision seems largely solved. Maybe that's, I know people are going to shoot me down if I say that. There are definitely advances to be made, but robot vision, computer vision, is very advanced compared to tactile sensing, where there's really nothing. It's just beginning. And one of the things that I'm realising is we don't even know what to do with the tactile data that we collect. So we're funding people to work on tactile sense data, but I think it's going to be helpful to try and form a common representation for all kinds of tactile data, whether that's from piezo-resistive sensing or optical sensing or electrical impedance tomography. There are lots of different approaches. And at the moment, I think there's a big sort of barrier towards anyone trying to use that data because they're like, what even is this stuff? What does it mean? If we could get it into a common representation that was pretty much agnostic to the sensor, I think that would be really helpful. And I'd like to fund some work on that for sure. Yeah, so going on with that, I think you're absolutely right that everyone recognises that the lack of data is a big problem in robotics. I don't know that I have a great answer to how we're going to solve that other than, through using things like imitation learning to have a starting point, which can then be refined, maybe through reinforcement learning in simulation, then in the real world, in environments where it isn't going to matter if you get it wrong.
Hopefully.
Yeah, exactly. You try it out first and then you get certain that you have a given performance level. But I think it's going to take a long time for that data flywheel to really get going and acquire enough data. It's such an open question at the moment, I think, how rapidly robotics takes off. And I see it maybe working first in relatively constrained environments where there's a relatively standard task. Like, say, electronics assembly, that's a use case that I think is interesting. It's a relatively constrained problem. You can say what components are, you can model it in simulation, and it's not a disaster if the robot makes mistakes. So that feels like quite a good initial use case. And the other problem with robotics is they're currently expensive. I think that's also something we need to change. But a lot of the applications people talk about robotics, it's just not really going to make sense economically because humans are really good and some humans are not very well paid. So, you can get a lot of human labour, whereas it's not economic to look at replacing that with a very expensive robot that's going to make a lot of mistakes.
Well, that's a question I wanted to ask you because, for instance, in a country like Japan, they are starting to think there are some voices saying, okay, we can overcome the decrease of population by leveraging robotics,
yes.
And that's an approach. But there is also a limitation because of these potential tasks that you can do and how precise you want to be, right? So how do you see that? How do you see that replacement in basic, manufacturing or tasks in general?
Yeah, I think I'm very motivated by the demographic shift that's underway. I think that really motivates the importance of robotics. So just to put this in context for your viewers who may not be as aware of this as people who work in robotics, we're really at the cusp of a turning point in human history, right? For our entire species history, the population's been going up pretty much monotonically, but that's forecast to end this century. Right? The UN reckons human population will peak in about 2085 and thereafter start going down rapidly. So we are going to need to think about how do we maintain our current prosperity and standard of living in a world where we cannot rely on large numbers of young people to carry out the labour that we have in the past. And I think robotics is going to be the answer there. But I think we need to think about how that transition is going to happen. And I imagine robots coming in and helping humans, first of all, with relatively high-value tasks like low-volume, high-value manufacturing, where a lot of the workforce currently is close to retirement age, and they're very skilled. But potentially we could get a robot to take over from that group as they retire. And I think then, as the data flywheel gets going and robots become more capable, you can spread it out into the rest of society. And I think we need to manage this transition carefully because, if you look at the past, when there's been waves of automation, that's often been very disruptive. And we clearly want to minimise the disruption. But in the past, and I believe in the future as well, it's been hugely beneficial and just like totally unlocked a step change in human prosperity and flourishing. And I very much hope we can achieve that again.
No, absolutely. I think it's the balance, right? And how do you do the transition in the balance approach? But it's a problem that needs to be solved because it's coming. So I want to ask you about something else you mentioned in the challenges at the beginning of talking about robotics, which is many of the robots are still, you need a human behind it, or you need to control it. Full automation is difficult. There is also a limitation of computing that also can be in the robot, because you cannot have the distance connection in the cloud. You need to respond right away. You cannot have even milliseconds of no reaction, because that can change everything. So is there any area there that we are missing?
I think there are a lot of areas we need to explore more. So this is probably going to be a long answer because I have a lot to say here. I think current robotics is often very over-engineered. And this is, again, one of the perspectives I have coming from neuroscience. You know, traditionally, robotics has been incredibly precise, sort of millimetre precision, very fast control loops, things happening at 2 kilohertz. People are telling me, well, you have to, otherwise it won't be stable. And I'm like, but human beings walk around, nothing in our bodies, with the possible exception of hearing, is happening at like 2 kilohertz, right? Our motor control loops are not that fast. We've got so much noise, so much latency, and yet we do really well, much better than today's robots. Or again, you look at insects, you think of bumblebees with 1 million neurons and the kind of complex behaviour they can carry out. And today's robots have got like shed loads of compute thrown at them, stacks of GPUs, you know, all these vast billion parameter LLMs, and they're still really clunky compared to animal bodies. So I'm thinking we're missing a trick here. And I think one of the things we're missing is morphological computing in the jargon. So the idea that you can, in fact, do a lot of the computation through the physics of the body. And I think this is a solution that evolution has discovered, you know, and exploited massively, because brains and bodies have evolved together over billions of years. You know, you look at insects, there's some great examples there. And we're not really exploiting that in today's robots. So another thing that we're funding in my programme is work on trying to co-design robot hardware, so the shape of a manipulator, for example, and the number of joints, along with a control policy, to try and use those same principles. Obviously doing it in simulation rather than billions of years of evolution, but trying to get that same simplification.
How much inspiration you take? You talk about insects, you talk about looking at evolution. How much inspiration your research areas, not just the ones you are funding in your spaces, are looking into evolution for that?
I mean, I find myself thinking about it all the time. So like tactile sensing, for example, you just look across the entire animal, or frankly even plant kingdom, everything is just covered in sensors for pressure and, you know, mechanical pressure, mechanosensors. They're ubiquitous. And so it's like over billions of years of evolutionary history, in every single possible ecological niche, there is no solution that doesn't use tactile sensing. And yet that's what we're trying to do in robotics. Right. And that feels like a very high-risk decision, right? Whereas vision, and I speak as a vision scientist, that's actually a pretty niche skill, really. You know, humans are incredibly visual creatures. We are, yes. But most animals are like legally blind by human standards. They've got incredibly low-resolution vision. So I think that what that says to us is that actually tactile sensing is more important in most situations than vision. And again, especially for dexterity, right? Vision is great if I want to know what's on the horizon that's going to be coming down the track towards me. But if I want to know what's right here, right now, then it's...
And react right away. I have the reaction and adaptability, right? That's the part that you were mentioning.
Exactly.
Wow, that's a lot of challenges you're working on. I want to ask you a final question about your program, just to say, because you talk a lot of things about, I'm also looking into that and funding. And there is something that you call opportunity spaces in the program. And that's not entirely just research. It goes beyond that. Sometimes it goes into rapid solutions. It can be more flexible. Can you explain a little bit what are those and what are the areas that you are exploring, others than what you mentioned already?
Absolutely. So this is how ARIA thinks about the problems it tackles. We're a small new organisation, so we don't have the resources to spread across the entirety of science and tile the space, as it were. So we identify a number of opportunity spaces, which are these areas that we think are important, underserved and ripe. So, for example, in my case, that was robot hardware, smarter robot bodies, as we named the space. And within that, we launched these discrete programmes that are focused on particular challenges, like robot Dexterity. And each opportunity space can have multiple programs. Because we're just starting out as an agency, we're about 3 years old, most of the opportunity spaces just have one program currently. Precision Neurotechnologies opportunity space is currently having its second program launching.
Congratulations.
Yeah, that's right. It's great. Congratulations to my colleague Jacques Carolan, who's led both those programs. I'm considering a second program within the Smarter Robot Bodies opportunity space, which might well be focusing on locomotion and trying to get efficiency gains in robot locomotion using some of the principles that we can take from biology again.
Well, wonderful. You are extremely busy and you have to think about a lot of things. And you are opening a lot of spaces and probably you are need to explore. And that's the reason you are here exploring in Japan right now. And so for people that are interested in this field and they are thinking similar to you and want to collaborate or reach out to you, what is the best way of collaborating with you, your programs and ARIA in general?
Yeah, ARIA in general, I'd say visit our website. We have a sign up for updates page, so you can give us your email address and say the areas you're interested in. And then when we launch a new call, you'll get alerted. So absolutely do that. We've got our second cohort of program directors are currently launching programs in a whole range of areas, including trustworthy AI and communication between AI agents, ecosystem resilience, platforms in the sky that can, aircraft that can stay up harvesting energy from the atmosphere, all sorts of areas. So there's a lot going on. So yeah, I would say sign up for updates, keep an eye open there. All the people that we fund are available on our website once we've signed contracts with them. So you can see who we're funding and obviously reach out to them. If they're working on something that you're interested in, then yeah, reach out.
What would be your advice for someone that is starting the research and is dreaming in like going into these frontier areas and exploring the way you are doing right now?
That's a great question. I think I would say keep your passion, follow your interests. I'd definitely say don't be afraid to be bold and do things that you think you can't do. I've changed area a few times. I did a doctorate in astrophysics, then I moved into neuroscience, and now I'm working in robotics. I think a number of times people have said, oh, you won't be able to do that. But, I managed to find a way. So I think, yeah, be bold, follow what you're interested in and just be really passionate about it and keep on going. And I think young people nowadays do have a great gift that it's easier than it's ever been to learn things and to find out, talk to a good AI about, your questions about science and so on, and so many amazing YouTube videos and that. So I feel like quite jealous compared to what was available to me when I was, say, doing my degree.
Yes, absolutely. It has changed a lot. But keep the resilience and be passionate about what you are doing.
Keep the resilience. That's a good.
Fantastic.
Phrase.
Well, thank you so much, Jenny. It was a pleasure to having you here. And thank you for sharing all this with us.
Absolute pleasure. Thanks so much for having me.
Thank you.